All right, here's the screencast for the second part of 6.1. Oh my god. Okay. Screencast for the second part of 6.1. So, solving an initial value problem. So notice we can't find a unique solution to a differential equation unless we're given further information, all right? That's why we had all these plus c's. We don't know what the constant is, right? We're unable to figure out like which one of these functions was our original one. You know, we say, okay, well, the derivative is 2x. What's our original function? What function's derivative is 2x? Okay, well, x squared plus 2, x squared plus 3, x squared, like we don't know. That's why we put a plus c, is because it's unknown what the constant is. So how are we supposed to find a unique solution? I could have a million that satisfy this dy dx is equal to 2x, right? X squared plus 1, x squared plus 2, x squared plus 3, x squared minus 50, x squared plus 100. I could sit here all day and talk about those. It'd be a really boring screencast. So we want a unique solution. So we have to be given further information. We have to be told what the initial values are. All right, so if the general solution to a first order, remember it's just the first derivative, first order is just the first derivative, is if the first order differential equation is continuous, the only additional information we need is the value of the function at a single point, called the initial condition. Once we know our xy coordinate of our single point, we can plug in, because we'll know the xy there, and then we can solve for what our c would be, right? A differential equation with an initial condition is called an initial value problem. It has a unique solution called the particular solution to the differential equation. So let's go ahead and let's do this example together. Find the particular solution to the equation dy dx is equal to e to the x minus 6x squared, whose graph passes through the point 1, 0. Awesome. So this is the x, y. I'm going to plug in at the end. But first, we're going to do what we just were in the first screencast. Right, dy dx is going to be equal to e to the x minus 6x squared. First step, multiply by dx on both sides. Right, so we have dy is equal to e to the x minus 6x squared dx. Next step, take the integral of both sides. All right, all we're trying to do here is solve for what our original function is. All right, so I have y is equal to, well, e to the x is the derivative of e to the x. Negative 6x squared is the derivative of, okay, add 1 to the exponent, divide by our new exponent. Let's see, so minus 2x cubed, right? Because we have negative 6x squared plus 1, so that's 3, right? It's a 3 over my new exponent 3. Okay, that turns into negative 2. Awesome. And then I have to tack on this plus c. But we don't have to wait too long because we have an x, y coordinate we can plug in and solve for what our c would be. So I'm going to go ahead and I'm going to plug it in. So my y is 0 equals e to the 1 minus 2 times 1 cubed plus c. Plugged in my x, plugged in my y. All I have to do is isolate and get c by itself. So this is 1 cubed is 1. So this is just e. 0 equals e minus 2 equals c. Move these to the other side, so I have negative, I'll write it as 2 minus e equals c. So I just have to plug that back in for my c, and my answer for my particular solution will be y equals e to the x minus 2x cubed plus 2 minus e, and that is my final answer, because remember the 2 minus e is equal to c, so that is what I put in place. And that's it. All right. Solve the initial problem explicitly. Okay, so we want the particular solution. We know what a is, we know what x is. Literally, this is like my point 1, 6. X is my 1, y is my 6, and here y is our a. Okay, so let me start by writing dA equals the integral of 10x to the 9th plus 5x to the 4th minus 2x plus 4 times dx. All I did was I multiplied by dx first thing. There we go. Let's take the integral. Okay, so I have a is equal to, so add 1 to the exponent, divide by our new exponent, so this just turns into x to the 10th power. Add 1 to our exponent, divide by our new exponent. Ooh, this turns into x to the 5th. Add 1 to our exponent, so This is x to the first, plus 1 is 2. Okay, divide by 2. Ooh, that just turns into negative x squared. And then plus 4, so it's a constant, so we tack on the x plus c. Okay, and if you're like, what? I don't know. Okay, if you take the derivative of this guy, you should get back the equation that we're trying to take the derivative of. All right, let's plug in our values. So a is 6 when x is 1, so 1 to the 10th plus 1 to the 5th minus 1 squared plus 4 times 1 plus c. So this is just going to be 6 equals 1 plus 1 minus 1 plus 4 plus c. Okay, so 1 plus 1 is 2, minus 1 is 1, plus 4 is 5, subtract from the other side, 1 equals c. So my final answer is going to be a equals x to the 10 plus x to the 5th. Oh my god. I'm sorry. I think the people above me in my apartment are moving. Or at least they're moving furniture all around. Okay, just rewrite it, but instead put this in place of my c. Alright, try the next one. So I'm going to multiply by dx on both sides right away. So dy is equal to 5 secant squared x minus 3 over 2 root x dx. Okay, take the integral of both sides. So I have y is equal to, oh yeah, and we have our initial y and x values. Okay, so I'm going to bring let's see. So I'll take it step by step. So when I have integral of 5 secant squared x dx, you can just bring the 5 out front and then take the integral of secant squared x dx. So the secant squared x is the derivative of tan x. So this is just going to be 5 times tan x. All right, this next part, I'm just going to bring the negative 3 over 2. Let's do it over here. Okay, so integral of negative 3 over 2 root x dx. Hey, okay, bring the negative 3 over 2 outside. Integral square root of x is just to the 1/2 power dx. So you add 1 to the exponent, which is x to the 3 over 2. And I'm dividing by 3 over 2, which is the same thing as multiplying by the reciprocal. And don't forget we have a negative 3 over 2 out here. So instead of dividing by 3 over 2, I'll multiply by the reciprocal, 2/3. Notice that goes away. I'm left with just negative x to the 3/2. And then tack on a plus c. Okay, let's go ahead. Let's plug in our original values, right? Y is 3, x is 0, so 3 equals 5 times tan of 0 minus 0 to 3 over 2 plus c. Okay, that's just 0. Tangent of 0 is going to be 1. No, tangent of 0 is 0. Sorry. Oh, tan of 0 is 0, so that's also 0. Wait, what? Did I write this down wrong? No. Okay. No, I'm good. Okay, so y is 3. So you get 3 is equal to c. So now we just have to rewrite our equation. So y equals 5 times tan x minus x to 3/2 plus 3. And then that's our answer. Cool. We have another one. Okay, so this is much easier. Split it up. So dy is equal to cosine x dx. Go ahead and take the integral of both sides. So you have y is equal to, let's see, cosine is the derivative of what function? Sine. So it's just going to be sine of x plus c. And when y of 0 is 1, okay, so that means x is 0. When x is 0, y is 1. Y is 1. So I have 1 equals sine of 0, because I'm plugging 0 in for x, plus c. Sine of 0 is 0, so 1 equals c. So I'll just write y is equal to sine of x plus 1. And that is the exact solution. This is how we would solve it with an indefinite integral, because we're solving for c. We're solving which sine function it's going to be. So remember, sine, let's see, 0, max, min. Okay, so this is just sine of x. And so the derivative would be cosine of x. It's talking about how it'll change. But the issue is, I could also have, let me duplicate it. I'm going to make it a different color. Okay, but I also, if I move it down just a little bit, that's another function, right? It's sine of x minus some number, but it also has the same derivative, right? The slope of my graph is changing. All right, let's duplicate it again, move it over, let me make it another color. I'm really trying to drive this fact home, right? You see, all of these are changing with the same rate, right? They all have the same derivative. They all have the same slope, the same change. But the difference is, are you shifted up, down, down, whatever. So the only difference between all of these is like the plus c. Am I shifting? Do I have a vertical shift up or down? This, by solving for c, we say, yes, this is the one. Everything is shifted. Oops, sorry. This is the one, right? Everything is shifted up by 1. Okay. Try to make sure we understand that. And slope fields. Since the differential equation gives the slope at any point, we can use that information to draw a small piece of linearization at that point, which approximates the solution to the curve and passes through the point. So repeating the process at many points yields an approximation called the slope field. Literally, we're going to be drawing the slope for every single point in our, every single x and y value. So the first thing we want to do is, okay, we know the slope is x over y. So I'm going to pick a point. I'm going to pick this point right here. And I want to know what the slope is. So I'm going to evaluate dy dx at, where should I start? So let's start somewhere easy, right? This is at 1, 2. So I'm going to start right there. At 1, 2. So I'm going to evaluate it. So I put in 1 for x, 2 for y. So that's a slope of a half. So let's see. This would be a slope of 1. A slope of half would be something along that. Okay, so it's a slope of a half. Something like that. Okay, let's evaluate it at 0, 2. Is this what I want to do? Yes. Okay, let's evaluate it at 0, 2. So x is 0, y is 2. Such as 0. It's a slope of 0. And if you think about it, all of these values along the y-axis, all of these values are going to have the same slope. It doesn't matter what the y value is. If x is 0, the top's going to be 0, and so the slope is 0. So actually, all of these slopes here are going to be 0. So we're just drawing what the slope would be at all these points. Okay, let's do this guy right here. dy dx, I'm evaluating the slope at -1, 2. So this is just going to be -1 over 2. That's just -half. Okay, so if this is a slope of -1, it's got to be about half of that, so it's about like that. Close. Something like that. Half. Okay, so we've gone across the top row. Let's come back here. I'm going to go 1, 1. dy dx. Evaluate at 1, 1. This is just x over y, so 1 over 1 is a slope of 1. So it's going to be steeper than our slope was at 1, 2. Okay. And then if I pick, let's see, we already have this guy in the middle. Let's pick this one. No surprise, it's going to be roughly the same numbers. The only difference is our x is going to be negative instead of positive, so it'll be a -1 instead. So this slope should be more negative than the one that was up here. So you don't have to, like, my intention is not for you to plug in every single one. Hopefully we can cut some corners like we did for all the x equals 0. What about when y equals 0? What about when y equals 0? So let's do 1, 0, right? At 1, 0, you get 1 over 0. Well, that's undefined, so you literally don't draw anything. So we're done with that x-axis row, and now I just need to go to the bottom. How about at 1, -1? Well, this is just going to be 1 over -1, so that's just a slope of -1. just like that. No surprise. If I come over to -1, -1, you have -1 over -1, which is 1. Okay, so that's a positive slope. So it's undefined here. You don't have to write undefined. Literally, slope fields, you don't actually see them written as undefined. This one should be undefined because it's 0 over 0. So I'll just leave that one alone. Okay. So I want to show you what an actual picture of, ooh, I thought I had an actual picture of a slope field. It's okay. On your homework, you have one. All right, dy dx is x plus y. Hopefully this one is a little better. I'm just going to pick the points and then draw what the slope would be. So let's pick 1, 2. So all you have to do is add it together. So it's a slope of 3, so it's really steep. If I pick this point, 1, 1, so you're adding them together, it's going to be still steep, but not as steep as the top one. And then 1, 0 has a slope of 1. And then you have 1, -1. When you add it, it's a slope of 0. So it should be 0, 1. There should be 2. And this is like slope of 3, so it's even steeper. It's kind of hard to tell the difference between them, but it should go flat to steep as you go up. Okay, remember, we're just adding these together. Adding x and y together. So, I picked this point, right? This point is 0, 2. If you add them together, it's a slope of 2. So this line and this line should match. These two lines should match. If I add 0, right, 0, 1, 0, 1, if I add these together, because it's x plus y, there should be a slope of 1. So this line and this line should be the same slope. And then 0 plus 0 is a slope of 0, okay. And if I take let's see, 0, -1, that's a -1 slope. And if I add them together here, it's -2, so it's even steeper. This is a -1 slope. If I go -1, 1, that's a slope of 0. And then this is going to be, let's say, -1, 2 is a slope of 1. So what you notice is along the diagonals, these all have the same slope of 1. These all have the same slope of 0. These have the same slope of -1. These have the same slope of 2. So there tends to be some patterns just depending on your differential equation that you have. Okay, so this is it for 6.1. Go ahead and try to do as much of 6.1 as possible. Then we will work on the worksheet in class. We definitely will not have enough time to do the whole worksheet in class, so try to do as much as possible beforehand.